Hi guys, Miss Peterson here, and welcome to a chemistry lecture on models of covalent compounds. In this lecture, we're going to be talking about Lewis structures and the shapes of molecules and how Lewis structures can both give us a lot of information and why sometimes we might want to use a different type of model, like a ball and stick or space filling. So let's go ahead and get started. So how do we model covalent compounds? We've already talked about the lattices for ionic compounds, and we've seen covalent compound models before in a lot of our videos. Let's look at methane as an example, okay? So we got the chemical from methane, CH4, and that is a very, very common way that we will represent methane if we want to know what atoms make it up. We also have the Lewis structure for methane right there, showing the carbon with a single covalent bond to each of its 4 hydrogen atoms. We got the ball and stick model, which shows us the tetrahedral shape of it, and the space filling model that gives us a sense of how those atoms actually take up space in their behavior. So zooming in on the chemical formula, okay, these are just easy to write. That is how we're going to represent it when we want to know what methane's made of, carbon and hydrogen, carbon and 4 hydrogen atoms, but we're just writing it quickly, okay? It doesn't really give us any information about the structure. For all we know, those hydrogens could all be in a line, okay? They're not, but you know what I mean, okay? So formula's great, but no structure information. Typically for structure information, the most common 2D representation is going to be the Lewis structure. And I want you guys to look at the Lewis structure compared to that ball and stick model, okay? They're both great, but the ball and stick, much easier to represent in 3D. If you use the PhET molecular shape simulation or any other chemistry type simulation, they're likely going to be using ball and stick type models. Where if you're looking at a sheet of paper in a report, in a scientific journal, and anything like that, it's most likely going to be the Lewis structure because it shows us all of the connections, much easier to represent in the 2 dimensions. However, if you were just looking at that Lewis structure for methane, you might think that it was all 4 like in a crisscross, okay? But it's not. It's actually got this sort of tetrahedral shape where it's kind of like a 4-sided pyramid with a triangle on each side, okay? So ball and stick, better at showing the shape. Lewis structures, better at representing in 2D. So what's the last one for the space filling model? Well, those ones show the relative size. These are used a lot in like the medical field when they're trying to figure out how a certain drug will interact with the body. They can look at the shape and how it folds and interacts with, say, the proteins or the neurotransmitters in your brain. And to do that, we might use a space filling model. Okay? It doesn't show the bond angles as well as the ball and stick model, so it's not used as much in simulations at like the general level. These are typically more specific. A lot of structures of like DNA and proteins and things like that use the space filling models. So how do we draw Lewis structures? Those are the ones that are going to be most common to draw and represent in 2D. So let's learn how to draw them. I'm going to give you guys a set of, I think it's 5 steps that will get you to the correct structure every time. And then I'll give you some hints and tips that can help you get to the structure faster once you get a little bit more comfortable with them. So step 1, like everything we do in bonding, we got to count up the total number of valence electrons in our model. And hopefully you remember from the periodic table that the valence electrons you can tell from the group or the column number on the periodic table. So if it's in group 1, it's got 1 valence electron, but none of those will be in our covalent molecules because those are all nonmetals. So it's going to be things like carbon, which is in group 14, meaning it has 4 valence electrons. Nitrogen is in group 13 or 15. Group 15, so it has 5 valence electrons. All of the halogens in group 17 have 7. Okay, so we just need to count up so we know how many electrons are going to be represented in our structure. Once we know that, we put the first element in the formula in the center, unless it's hydrogen, okay? Hydrogen is going to be an exception to a lot of things in Lewis structures because it's only 1 proton and it's only got 1 electron. So it only has access to its first energy level, meaning it can only form ever 1 bond. So if you can only make 1 connection, you're not going to be the center of attention, okay? the center of attention has to be able to make multiple connections. So we are going to connect the other atoms to that central atom with single bonds to start. Okay, and now remember, a single bond is just a single line on the Lewis structure. Okay, and that line represents 2 shared electrons. Once you have all of the other atoms connected, and they're all connected to that central atom, you're going to fill in the rest of your electrons as lone pairs. Now, remember, lone pairs are 2 dots. Okay, we'll always have our electrons paired up, and we start from the outside in until each atom is stable. Now, the atoms are stable when they have that full NS2 NP6 energy level, okay? That full octet of electrons. So they're looking for 8. So we want to do that until each atom is stable or until we reach the total number of electrons that we counted up in step 1, whichever comes first. And remember, hydrogen is an exception to this. Hydrogen will only ever have a single bond connected to it. Hydrogen will never have any lone pairs. Okay. Boron is also an exception you might see, but it's much less common in our chemical compounds. Now, if we've reached the total number and not all of our atoms have an octet yet, again, remember an octet means 8 valence electrons, then we're going to be moving electrons from those outer ones, okay, from lone pairs to being a shared pair until everybody's happy. Okay, so some hints and tips that we will also use to help out is we need to remember that covalent bonds typically form from the unpaired electrons. So if you draw a dot diagram and know how many unpaired electrons the atom has, you can predict how many covalent bonds it most commonly forms. So my example for this is hunk 1, 2, 3, 4. Okay, and you have to say it like that. Hunk 1, 2, 3, 4. And what this tells us, is that hydrogen only has 1 electron. So it tends to form 1 bond. Where oxygen is in group 16 of the periodic table, so it has 6 valence electrons. And if you remember, electrons are negative, they repel each other, so we fill in 1 per side until they double up. So there's our 6 electrons, and we can see that there's 2 unpaired ones, meaning oxygen tends to form 2 bonds. So hydrogen forms 1, and oxygen forms 2. Okay, and then if we look at nitrogen, nitrogen is in group 15, so it's got 5 valence electrons. 1, 2, 3, 4, 5. So nitrogen tends to form 3 covalent bonds. And last but not least, we have carbon. Carbon has 4 valence electrons because it's in group 14. So carbon tends to form 4 connections. And this makes sense, okay? You often hear that we are carbon-based life forms, or that all of the stuff on, all of the organic things on Earth are carbon-based. And that's because of carbon's amazing ability to form 4 bonds. No other element on the periodic table can do that as easily as carbon can. So carbon, with all of the connections it's able to make, forms the basis for our proteins and our fats and our carbohydrates and the nucleic acids in our brain and all that kind of stuff. Okay, cool? Okay, cool. Now, one other hint and tip is when in doubt, try to make it symmetrical. And just remember that that magic number is 8, except for hydrogen. But except for hydrogen, all atoms want to be surrounded by 8 electrons, whether that's 4 bonds, 4 shared pairs of electrons, or some lone pairs of electrons, okay? So let's go ahead and do some examples. For both of these, I'm going to show you guys how first using the steps, and then how you might do it if you were doing it like a puzzle using some of these tips and tricks of the unpaired electrons, okay? So H2CO, more commonly known as formaldehyde. So we got our chemical formula there. Step 1, we got to count up our number of valence electrons. So hydrogen has 1. So hydrogen has 1, and we have 2 hydrogens, so I'll just go 1 plus 1. We got a carbon. Carbon is in group 14, so it's got 4 valence electrons. And oxygen is in group 16, it's got 6. So in our structure, we should have 10, 11, 12 electrons represented, okay? Now, step 2. The first element in the formula goes in the center unless it's hydrogen, okay? It is hydrogen, so we go to the second element, and that is going to be carbon. Okay? Last step, connect them all with single bonds. Connect the rest of the atoms with single bonds. So we have 2 hydrogens, hydrogen, hydrogen, and 1 oxygen. Now, it doesn't matter if you put them like that, or if you put them like this, okay? Or if you put them like this, okay? Doesn't matter at all. We typically do want to spread things out as far as possible because that's going to be more similar to the actual shape of the molecule, okay? So far in our picture, I got my 2 hydrogens connected. I got my oxygen connected. Just for drawing around and showing you guys things, I am going to move the oxygen to this side so it's separated from those hydrogens a bit. But right now in our picture, we have 2, 4, 6 electrons, meaning I have 6 more to place. So step 3, we place them from the outside in until each atom has their octet, except for hydrogen. So we can't put any lone pairs on hydrogen. So I'm going to put my 6 more on oxygen. So oxygen has 2, 4, 6, 8. And now that oxygen is happy because it's surrounded by 8 valence electrons. The hydrogens each have 2, and so they're happy. And if I'm counting it up, I got 2, 4, 6, 8, 10, 12 total electrons in my picture. But I'm not done quite yet, okay? Our carbon isn't happy yet. The carbon only has 6 electrons surrounded it, those 3 shared pairs. Now, carbon wants to have 8, but we're out of electrons. So we're going to take one of our lone pairs from oxygen, and we're going to move it to create a shared pair, creating a structure like this, with a double bond between the carbon and the oxygen. Since that lone pair became a shared pair, I didn't change the total number of electrons, but now the oxygen has 2 shared pairs and 2 lone pairs around it. And if we look at our total structure, I'm just going to count up my electrons real quick. I got 2, 4, 6, 8, 10, 12 electrons, which is how many I was looking for. Okay, cool? Okay, cool. Now, let me show you how to do it using that whole idea of unpaired electrons and kind of treating these like a puzzle, okay? So we know that it is the unpaired ones that get shared. So I'm going to draw dot diagrams over here for each. Let me go ahead and separate it. Okay, method 1 on the left, method 2 on the right. Each of them into just showing their dot diagram so you guys can kind of see it. Okay. Now, remember in this one, each dot represents an electron, and it is the unpaired electrons that become shared pairs. So each dot is really counting up our 12 valence electrons. And then it's a puzzle to figure out who goes with who. So if I'm looking at this puzzle, okay, the carbon has 2 spots, or I guess 2 spots for that hydrogen to go. So those can create a shared pair, and those can create a shared pair. And then we got the oxygen. It wants to form 2 bonds. Carbon has 2 more unpaired. So those can create a shared pair, and those can create a shared pair. In fact, some people even represent their Lewis structures like this, okay? It is another representation you might see using the dots instead of the lines. So if I were to do it that way, I would put the oxygen here, okay, creating those 2 shared pairs. And then we have the hydrogen. And then we have the hydrogens. Creating that shared pair there and there. So you can kind of see where the bonds come from. So each of these shared pairs becomes a line. And so we have the hydrogen connected to the carbon, connected to the hydrogen, with two lines connecting it to the oxygen. Okay. So just another way to represent that you might see. Okay, cool. Okay, cool. Let's try another one. H2O, water. Okay, one of our most common ones. So let's go ahead and count up our valence electrons. Hydrogen has 1, so we got 1 plus 1 for 2 hydrogens. And then we have an oxygen atom that has 6. So 6, 7, 8. We should have 8 total electrons in our structure. Okay. Now, we put the first element in the formula in the center. Unless it's hydrogen, it is hydrogen. So I'm just going to put the oxygen there and then put my 2 hydrogens. And now I have 4 electrons represented in my structure. Okay, 2 and 2. So I got 4 more to place. The hydrogens can't take them, but the oxygen needs 4 more electrons in order to be stable and have its 8 valence electrons. So I'm going to put 2 lone pairs there and there. Okay, now do a quick count. We got 2, 4, 6, 8 total electrons in our picture. And there we go. Okay. Now, just to show you if you did it the puzzle way, we have oxygen with its 6 valence electrons. Okay. And then we have the hydrogens with their 1 each. So you can picture the hydrogens coming in and filling in those gaps. Okay. Now, I do want to show you guys that these 2 structures, okay, whether it's like this with 2 lone pairs on top and bottom and the hydrogens on the side, or whether it's like this one, okay, both of those structures are equally correct, okay? They're both showing the 2 connections, the single bonds from hydrogen to oxygen, and the 2 lone pairs. When we talk about shapes in a couple slides from now, we'll talk about why one of these is a little bit better than another. But they are both perfectly correct Lewis structures for water. Okay, let's go ahead and do one more example. Okay, carbon, oxygen, chloride, dichloride. Yeah, it's something. Okay, let's go ahead and count up our valence electrons. We got carbon has 4. Oxygen is in group 16, so it's got 6. And then chlorine is in group 17, so it has 7. And we have 2 chlorine atoms, so 7 plus 7. For a total of 14 plus 10, 24 valence electrons should be in our structure. So a little bit bigger one than the ones that we've done before. But let's go ahead and follow the steps and get it going. Yep. So first, we put our carbon in the middle. Okay, it's the first element in the formula. We're going to start by connecting the rest of them with single bonds. So I'll go oxygen and chlorine and chlorine. Okay, so there's 6 electrons. I have 24 to place. All of the outside ones still need more electrons. So I got 6, 8, 10, 12. That chlorine's happy. 14, 16, 18. That chlorine's happy. 20, 22, 24. That oxygen is happy and I'm out of electrons. But my carbon's still not happy. What do we do then? Okay, yep, the last step. In order to make the carbon happy, we're going to move one of oxygen's lone pairs to create a shared pair. So I'm just going to erase it from there and add a double covalent bond instead. Okay, double covalent bond, which means there's 2 shared pairs for a total of 4 total electrons shared between that carbon and oxygen. Okay. And again, if we were doing this the puzzle way, okay, we would see that carbon has those 2 or 4 connections. Okay, chlorine has 7 valence electrons, so it has 1 unpaired one. So it likes to form its 1 unpaired one with those carbon unpaired ones, which leaves our oxygen, okay, with its 2 unpaired electrons, go zoop, zoop, and its 2 lone pairs, okay, creating the double bond there and the 2 single bonds that become up there. Okay, cool. Okay, cool. Lewis structures definitely take a lot of practice, and I recommend just trying to do as much as you can to see as many as possible, okay? The more you're familiar with them, the more you'll develop your intuition for which structure looks right and wrong and how these work. But you can always fall back to the steps. What about the shape, though? Okay, the shape of a molecule. Well, when atoms arrange themselves into a molecule, okay, it's their electron clouds that are arranging and combining, and electrons are all negative. So they will always spread out to maximize the distance between their atoms, okay? Make the maximum distance, okay? It's not like these 4 are going to be squished over here on one side together, okay? They're going to repel each other and spread out as far as they can to minimize those repulsions. Now, what we call the study of molecular shapes is called VSEPR. It stands for Valence Shell Electron Repulsion Theory, and it's basically a set of rules that we use to determine the shapes of molecules. And why the shape of a molecule matters is because it helps determine if the molecule is going to be polar. Okay, now polar molecules like water can do a lot of cool things. It increases their surface tension, their boiling point. They're more likely to be liquids or solids rather than gases. Okay, polarity determines a lot about the properties of a molecule. So if it is a completely symmetrical molecule, like this model of methane, CH4, that I have here, it's going to be nonpolar. But if we have an asymmetrical molecule where there's one area with more electrons than another, then it's going to be a polar molecule, okay? So asymmetrical, polar, symmetrical, nonpolar. So here is some examples of those. So you can see things where we have the same atom. That's perfectly symmetrical. It's going to be nonpolar. Carbon dioxide is a great example because each of those oxygens are pulling in opposite directions, okay? Or just something that's completely symmetrical. Now, you can see here that that shape might be a little bit misleading, which is hard when you're representing a 3D shape in 2 dimensions. Where polar ones, there's going to be some imbalance, okay? Like chlorine has more electrons than hydrogen does, so it's going to be negative, okay? We'll talk about water in a second. Nitrogen has a lone pair on top of it, which pulls that electron density up, okay, and creates a polar molecule. Now, what the names of these shapes are and how we use them is something called a VSEPR chart. Okay, now this I highly recommend printing out and having readily available whenever you're looking at molecules and trying to determine their shapes. It's based on the number of electron groups around it, so like how many there are. Okay, the only thing here is that if it's a double bond, that's going to be 1 electron group. So basically think of it as either lone pairs or connections. Okay, so that's a double bond on an 11, or a single bond, or a lone pair, or a double bond, or a triple bond. Those are all considered 1 electron group. And then we have our number of lone pairs. So what we're going to do is we're going to use this chart to determine the shapes of the molecules that we drew earlier in the lesson and determine if they're polar or nonpolar. Okay, so let's go ahead and look at the first one that we drew. Okay, formaldehyde. Here we can see it has 1, 2, 3 connections, 3 electron groups around it, and there are no lone pairs on the carbon. Okay, when we're looking at the molecules, we're looking at that central atom, so we're looking at that carbon. So if we have 3 lone pairs or 3 electron groups and 0 lone pairs, it is going to be trigonal planar. Okay. So this one is trigonal planar. And is it symmetrical? No, okay, we have that oxygen. That oxygen atom has more electrons than those hydrogen atoms. So that area of the triangle is going to have more electron density and therefore be slightly negative. This molecule is going to be polar. Okay. Now, let's look at water. Water has two things connected to it and two lone pairs. So if we go to our VSEPR chart, okay, it has four groups around it, two bonds and two lone pairs, and then two lone pairs. So that one is going to be angular or bent, okay? So if it's angular or bent, which model is a better model for it? Which Lewis structure is better? Yeah, okay. This one better shows the shape. It's not that the other one is wrong. It just can misconstrue the shape. Okay. In reality, those hydrogen atoms would be facing slightly toward you and the lone pairs would be slightly away, creating that imbalance. Kind of like this, okay? So you can see how it has that bent shape. You can picture the lone pairs being right here, okay? So the sideways one, slightly better representation of the molecule shape. And water, because it's asymmetrical and we got that oxygen up here with its lone pairs, the hydrogen's down at the bottom with no lone pairs, we have more electrons here, making water polar. Okay, water is polar, and that is the reason that water can be the basis of our society and climb up to the tippy top of trees and freeze from the bottom down and have high surface tension and all of the cool things that water does that makes it different from some other liquids. Now, last but not least, let's look at COCl. You might notice that this one has a similar shape to what other one? To that formaldehyde, okay? It has the three groups around it, one of them being a double bond, but it is also a trigonal planar molecule, okay? This one is also trigonal planar. And because we have those two chlorines that are super electron dense, it is a polar molecule. Okay, cool. Okay, cool. And that's all about molecules and their shapes. Okay, cool. Okay, cool.